Hi dear students, welcome to the 8th video lecture for the subject EC304 VLSI. So this is going to be the second part of module 6. Once again going through the syllabus of module 6. So in first part we have already covered the basic adder concept, the basic full adder truth table, the expression for full adder using the intermediate signals such as propagate, generate, delete signals, and we have studied how to realize static adder, how to realize dynamic adder. Then we have learned one carry circuit optimization adder configuration, that is carry bypass adder. So in this video lecture we will learn the remaining circuit optimization adder configuration, that is carry select adder. The carry select adders are of two types: linear carry select adder and square root carry select adder. So in this video lecture we are going to see these two main adder configurations and one more, that is the carry look ahead adder also. So we are going to see what all things: carry select adder. Main topic is carry select adder. Carry selector of two types: linear carry select adder and square root carry select adder. Moving on to the first one, that is linear carry select adder. So before that, what is the feature of a ripple carry adder? In ripple carry adder, every full adder has to wait for the incoming carry before an outgoing carry can be generated. So one way to reduce this delay by calculating both the possible values of input carry. So what are the possible values of input carry? It will be either 0 or 1. So we need to pre-calculate the sum value for both possible values of carry in. That is, for both 1 and 0 we will pre-calculate its sum and carry out. Okay, so we will evaluate the result for both possible values in advance. That is one feature or one key point to reduce the delay in ripple carry adder. Once the real values or once the real carry in comes, the correct result, we have already calculated the sum and carry out for the two possible values of carry in. Once the real carry in comes, we will only function or only computation remaining is to select the appropriate values only based on the incoming carry. Thus the feature of carry select adder is that the carry select adder will already calculate carry out for both Cin equal to 0 and Cin equal to 1 values and stores in a mux. And once the real value of Cin comes, the mux just selects the correct Cout value for the respective data input. So moving on to the figure for carry select, linear carry select adder. So we have a setup stage as the first block. So as we know, setup stage is a block that represents the generation of intermediate, carry out intermediate signals like propagate, generate and delete signals are generated at this block. Then based on that we will actually generate the 0 carry propagation and 1 carry propagation. Actually this will calculate the sum and carry out for the possible 0 value, and this block will calculate the sum and carry for the 1 possible value. Okay, and we will store it here, and as the carry in comes, the multiplexer will select from either 0 carry propagation or 1 carry propagation the values to the corresponding sum block and to the carry out path. Okay, so this figure represents actually the kth stage of a carry select adder. Kth stage means, for example, for a 16-bit adder we will divide it as 4 stages, with each stage handling 4 bits. So in this stage the bits under consideration are k, k plus 1, k plus 2, or k, k1, k2 and k3. Okay. The input carry of the kth stage comes from the or will be the output carry of k minus 1 stage. So that's why it is written as CO, k minus 1. During the wait time period of this stage, it will already calculate the output for carry in equal to 1 and carry in equal to 0. And as the original input comes, the multiplexer will select either the 0 or 1 output values cases, and the outputs, the output carry and the sum values. Thus when compared to previous adder, that is carry bypass and triple carry adder, the full adder will already calculate the output carry and sum values for both cases of input carry, and as the original input carry comes, the adder will just select the required output signals. Whereas in a ripple carry adder, the full adder will have to wait for the carry in to come for the calculation of sum and carry out values, and this the carry select adder reduces considerable amount of delay. So that is a summary of linear carry select adder. Consider the block of adder which is adding the bits k to k plus 3. So that is what actually shown here. Instead of waiting an arrival of the output carry of k bit k minus 1, both 0 and 1 possibilities are analyzed. Possibilities of full adder outputs are analyzed. When k0 comma k minus 1, or so when the input carry, that means C0 comma k minus 1 comes, either the result of 0 or 1 path is selected by the mux. The worst case propagation delay for the linear carry select adder is given as T setup, that is the setup time, first block, time to calculation, time for computation for the first block, plus n by m into t, where n represents the total number of bits and m represents the number of stages. This is actually T mux, okay, n by m into T mux. So T mux is actually time taken by a mux to select the output lines. Then comes m into T carry. T carry is actually the delay of the carry through a single full adder cell, plus T sum. T sum time to calculate the sum value for the final full adder cell. So that is this is the equation. You need to by heart or you need to understand the equation, propagation equation, or time required for propagation through the critical path. You need to understand and study the equation for each type of adders, because that is very crucial in while writing the answers. So this figure actually represents a 16-bit carry select adder. So 16-bit means how many stages? There will be 4 stages, each stage handling 4 bits. Okay, simultaneously, so first stage will handle the bits 0 to 3, second stage will handle 4 to 7, next stage will handle 8 to 11, and final stage, fourth stage will handle 12 bits from 12 to 15 position. So simultaneously all the bits are given to the corresponding to each of its full adder. Thus every full adder will do a pre-calculation of its sum and carry out value for both possible values of input carry, that is 0 and 1. So that is what 0 carry and 1 carry block represent. As Ci, 0 comes, the first stage will output its corresponding stored value of sum, and 0, 3 will be available for the next stage. Okay, so the output carry from this stage will be actually 0, 3, because the last bit handling is here 3. So that is available as carry in for the next stage. So this stage will already during this waiting period will already pre-calculate the sum and carry out values for its 0 and 1 possible values. So as the 0, 3 comes, it will do this mux will just select the appropriate path for of 0 or 1, and it will do output its sum, and it will output its output carry, which is actually 0, 7, because 7th bit is the last bit it is handling. For the other stages also, the output carry from the third stage will be 0, 11, and the output carry from the fourth stage will be 0, 15. Okay, so as Ci0 comes, first stage will output its corresponding stored value sum, and 0, 3 will be available. That's what I have said now. The select adder needs only time to select, whereas ripple carry adder will start to do the computation only once the input carry is available. So carry select adder is having that advantage. It is saving a considerable amount of time by doing the pre-calculation. Okay, so summary of 16-bit carry select adder. Simultaneously all bits are given to the corresponding to each of its full adder, and every adder will do the pre-calculation of its sum and carry out value for both possible values of input carry, that is 0 or 1, and the carry select adder needs only time to select the result. Okay, so that are the key features of linear carry select adder. So with that idea in mind, moving on to the next type of carry select adder, that is before that we have here shown the critical path. So this is the first step. So the time taken is actually this one. Okay, m into t mux. So mux t mux actually represents the time taken by one mux, okay, by a mux to select the output lines. Then t carry actually represents what? The delay of the carry through a single stage, that is actually t carry. T setup is the carry time, the initial setup time to calculate the carry intermediate signals, and t sum is actually the time to calculate the sum value for the final full adder cell. Actually there is a confusion. In the previous equation I have written as n by m into t mux plus m t carry. So I will clarify it later. Okay, in the note I have written it as n by m into t mux plus m t carry, but for this slide it is actually in the opposite way. Okay, let us anyway proceed to the next way. This is the figure for, this was a figure for the linear carry select adder. So by t equal to 8 here only how many bits are calculated here? Okay, or we can by t equal to 9, how many bits it is calculated? It is calculated only 16 bits, whereas in square root carry select adder by tp equal to or time period equal to 8, it has handled 20 bits. So that is another point which boosts the key point that square root carry select adder seems to be faster than linear carry select adder. I hope all of you understood the key difference between the linear carry select adder and the square carry select adder. The summary of square root carry select adder. So that here the delay can be reduced progressively by adding more bits to the subsequent stages in the adder, requiring more time for the generation of carry signal, or we can say that thereby avoiding the waiting time period for each stage. So for that we have allotted for the first stage 2 bits, the second stage 3 bits, fourth stage 4 bits, sorry, third stage 4 bits, fourth stage 5 bit, then fifth stage 6 bits, etc, etc. Okay, so next slide explains the delay calculation for the square root carry select adder. So let n bit adder contain p stages, and first stage adds m bits. Okay, m bit adder contains p stages with m bits, and with the first stage contains n bits. An additional bit is added to the subsequent stage. So we can write n equal to, n represents the total number of bits to be added. So n is equal to, so the first stage is handling m bits, second stage is handling m plus 1 bits, third stage is handling m plus 2. So each stage is handling different number of bits. That is a key point in square root carry select adder. So togetherly we can write it as plus etc up to m plus p minus 1. Okay, or we can write if we add this all together, mp plus p into p minus 1 by 2. If we expand this and rearrange, we will get p square by 2 plus p into m minus 1 by 2. If m is much less than n, for example, suppose the number of bits handled in the first stage is only 2 and the total number of bits to be added is 64, So that case m is much less than n, then the first term dominates in this equation number 1. So only one, the first term has to be considered, that is n is equal to p square by 2. That is approximation. N is equal to p square by 2, or p is equal to root of 2n. Okay, so then that case we can write like this: t setup plus mt carry plus root of 2n t mux. So in the previous equation for linear carry select order, we have written it as t setup plus mt carry plus n by m. So n by m is actually p itself. So that is equal to, that can be replaced as root of 2n into t mux plus t sum. So we had one confusion in the slide. Previous slide it was written like n by m into t carry plus m t max. So that is not actually the correct. So this is the actual correct equation itself: t setup plus m t carry plus n by m t max plus t sum for linear carry select order, and for square root carry select order, that n by m will be replaced with the value of p, and the value of p for square root carry select order for the condition m much less than n is actually root of 2n. That is, the delay of the square root carry select order is proportional to the square root of total number of bits. Okay, so here n represents total number of bits, m represents number of bits, actually not per stage, it is actually number of bits in the first stage, because in the second stage it is m plus 1. Okay, p represents the number of stages. Okay, so this is the comparison between different orders. You can see here for the ripple carry order, the propagation delay is actually, or the propagation time period is actually increasing with the increase in the number of bits. Whereas in case of linear carry select order, it has got a staircase waveform. It is gradually increasing as the number of propagation delay increases with the number of bits. Whereas in case of square root select order, that increase in the propagation delay is gradually gets flattened as the number of bits increases. So we can say, if we compare these three cases, square root carry select order is having less delay, or it is much pretty faster than the other two order configurations. So with that, our carry select order topic is over. So hope all of you have understood the key concept behind the linear carry select order and the square root carry select order. So in square root carry select order, we are actually avoiding the waiting time period when compared to the linear carry select order. And if we compare the ripple carry order with the carry select order, we are actually avoiding wastage of time by doing the pre-calculation of sum and carry out for the two possible values of carry in, and as soon as the carry in comes, the mux will do just the selection operation only. Okay, so that are the key points to be remembered till now. Okay. So next comes the second category, or the another type of adder, that is carry look ahead adder. It is also another adder configuration. Okay, this is not actually mentioned in our syllabus, but it is also an important adder configuration. So we will just refresh through the basic concept. So it is a fast parallel adder actually, as it reduces the propagation delay by more complex hardware. Hence it is costlier. As we make the hardware more complex, the cost becomes increases, or cost will get increases. So once again, recollecting the ripple carry adder. So this is the once again recollecting the ripple carry adder structure. So for each adder block, the two bits are to be added are available instantly. For every full adder case, full adder stage, the input bits are available instantly. However, each adder block waits for the carry in from the previous stage. So it is not possible to generate the sum and carry of any block until its input carry comes. Okay, so CLA, that is in carry look ahead adder, this carry propagation delay is reduced. For that you need to recollect in terms of our carry out intermediate adder equations. So we had the expression for carry out as AI bi plus, or carry out is here represented as Ci plus 1, that is the next Ci plus 1 input carry for the next block, AI bi plus Ci into AI XOR bi. Okay, and we had 3 intermediate signals generate. What is the expression for generate? Generate is actually A into B, and the expression for P propagate signal is A XOR B, and the expression for delete signal is A bar B bar, which is not actually used. So using this intermediate signal we can rewrite the expression for C out as Gi plus Pi Ci, and the sum as Pi XOR Ci. So for a 4-bit adder case, the first carry C1, the output of first carry block or first stage, that is actually can be written as, using this expression you can written as G0 plus P0 C0. The expression for C2 can be written as G1 plus P1 C1, and if we substitute it for C1 from the previous equation, it will be G1 plus P1 G0 plus P1 into P0 Cin or C0. And in case of C3 it will be equal to G2 plus P2 C2, that is actually, if you substitute for C2 here, that is G2 plus P2 G1 plus P2 P1 G0 plus P2 P1 P0 C0. And finally case of C4 it is G3 plus P3 C3, and if we substitute for C3 from the previous equation, the equation for C4 is G3 plus P3 G2 plus P3 P2 G1 plus P3 P2 P1 G0 plus P3 P2 P1 P0 C0. Thus from the equation we can see that C4, that is the output carry from the last stage, does not have to wait for C3 and C2, that is the previous output carry from the previous blocks to propagate. But actually C4 is propagated at the same time as C3 and C2, and this is actually an intuition actually, okay, based on this equation. So by doing some hardware realization we can achieve this. That means we not need to wait for the previous carry. All the carryouts can be obtained simultaneously, thereby obtaining the sum at a much faster rate. A bit delay is there. Okay, so this is a structure for a carry look ahead adder. We can consider the carry look ahead adder made up of 2 parts: the part that computes the carry for each bit, okay, this is that case, carry for each bit, and the part that adds the input bits and carry for each bit position. Okay, so the sum can be obtained. So P is actually A XOR B. Okay, so P0 is A XOR B0, P1 is A1 XOR B1, and Pn minus 1 is An minus 1 XOR Bn minus 1. And as soon as Z0 is available, we can obtain S0, S1, etc. up to Sn minus 1 using the basic Boolean expression for C0. Ci plus 1 is actually what? Gi plus, what is Gi? Ai Bi plus Pi into Ci. Okay, that is the disadvantage of carry look ahead adder. Behind the advantages of carry look ahead adder is the propagation delay is considerably reduced, because here the similar to the ripple carry adder, we need not want to wait for the output carry from the previous block to come. Rather, we are doing the calculation using the very initial carry inputs itself. Okay, so it provides the fastest addition logic. The disadvantage is that the carry look ahead adder circuit gets complicated as the number of variables increases. The circuit is costlier as it involves more number of hardware. To realize the above circuit concept, we require a number of AND and XOR gates, So as the number of bits increases, and more number of AND gates and more number of XOR gates has to be hardwarely realized, so which increases the cost for this adder configuration. So that's all regarding the adder design from module 6. So with that we have covered the basic adder design concepts, that is static adder, dynamic adder, carry bypass adder. So another name for carry bypass adder is carry skip adder. Then we have seen the circuit optimization adder configuration, that is carry select adder. And we have seen two types of carry select adder, linear carry and square root carry select adder. And finally we have seen one major adder design, that is carry look ahead adder also. Okay, so in that topic we will cover one more part, Array multiplier, which is module 6 to be covered, module 6. So hope you have understood everything. If you have any doubt, please free to call me or please mail to me. Thank you all.